folks, it is part 3, dipoles, and this is where we're going to finish up thinking about how molecules interact with each other, and specifically going over in detail how the balloon water demo worked today. So the first thing that we're going to do is I'm going to have you divide your notes in half, because on one half we're going to talk about dipoles, and then the other part will be for the demo. So over here on the left, we'll start thinking about dipoles. Now that we've been thinking a lot about polar things and nonpolar things, dipoles is kind of the final piece of that puzzle. So the easiest way to talk you through these is to just show you an example. Let's do hydrogen and fluorine. You should hopefully be comfortable with now looking at an electronegativity chart. Remember, fluorine is the sexiest element there is, which is going to give it a little partial negative charge. Hydrogen will have a partial positive charge. When we're talking about a dipole is an arrow that we draw to represent these shapes. So to draw a dipole for this bond, I would start with my partial positive and draw an arrow pointing at my partial negatives. And the final little piece is to stick a little crossbar on that. And the way I like to remember it is that it looks like kind of a little plus sign right here, which should be by our positive part of the molecule. So again, just one more example. If we did chlorine and carbon, carbon is our partial positive, chlorine is our partial negative. We would draw our dipole arrow pointing that way. And the last little thing to know about dipoles is that they indicate our partial positive and our partial negative ends of a bond. And that just comes in handy when we're thinking about, again, different polarities and whether things will be attracted to other things or not. Okay, so that's dipoles. On the other side here, let's think about our balloon demo. And we're going to look at two scenarios because if you remember, I showed you two different things with this balloon. The first thing that we looked at was water. And then the second thing that we looked at was some cooking oil. Both in a burette, both kind of streaming down and in some cases either interacting or not interacting with this balloon. So if you remember, in each case we had a balloon, so let's draw our little balloon here. A balloon that we had rubbed enough times to give it that static charge. And if you remember right, when we do something and we give something static charge, we're really just giving it a bunch of electrons. So in each case, we had our little static filled balloon, which was really just a balloon with electrons all along the outside. So And so in order to explain what happened, we need to think about what was happening with these molecules in each case. So let's kind of divvy this in half here. Let's first start thinking about the water. Our water molecules have an oxygen, two hydrogens, and if you were in class today, you should be aware that our oxygen has a partial negative charge and our hydrogens have a partially positive charge, and that's going to change how this molecule interacts with this balloon. I know that because our hydrogen has an electronegativity value of 2.1 and oxygen of 3.5. So there's a very, very big difference in electronegativities. That's why we say that water is a polar molecule. So again, imagine if a bunch of this water, all these molecules, are streaming down and we bring this electron-filled balloon close to that water. Again, from today you should feel comfortable with the idea that opposites attract. And so what will happen is that these water molecules will orient themselves so that all of the hydrogens, right? Because those hydrogens have a little bit of a positive charge and positives are going to be attracted to negatives. So we have all these water molecules that are going to want to bend, and the hydrogens are going to attract towards the electrons. I realized I said a second ago that atoms bend. The atoms don't necessarily bend. The water molecules reorient themselves, and so you can imagine that stream of water coming down. As soon as they get to that balloon, they go ahead and attract because we have that positive and negative charge interaction. So that's water. Water's polar, so it will behave differently when we bring it next to something with a lot of electrons. Let's think about oil next. Oil is made up of a carbon chain. I'm just going to put dot, 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 because the oil molecules go on forever. They're really big. And it's carbons surrounded by a bunch of hydrogens. To look on an electronegativity chart, hydrogens have our electronegativity of 2.1. Carbons have an electronegativity of 2.5. It's not that big of a difference. Because it's not that big of a difference, oil is classified as nonpolar. And that ends up being a really important idea to explain the behavior that we saw, why these molecules didn't do anything. So again, think about it. If something is nonpolar, that means that we do not have a partial negative and partial positive end in our molecule like we did with our water. Oil doesn't act like a magnet, which means if we bring it close to a balloon filled with electrons, there's no attraction there. There's not going to be this opposites attract because the oil doesn't have any charges. It has no partial charges. So it doesn't matter how much static we put into our balloon. No partial charges means that there's no attraction and oil is nonpolar. So that explains, again, why the water bent towards the balloon and why the oil did not. Okay, once you have this part, that is the end of that, and you are good to go.